everyone, you're watching the 29th video in the series Mathematical Methods for Economics. In this video, we will be talking about polynomial approximations to a function. We will specifically cover linear approximations, quadratic approximations, and even higher order polynomial approximations to a given function. In fact, these kinds of approximations are helpful as calculations are simpler with polynomials than for other types of functions. It may also be that you might be working with a polynomial itself, and depending on the kind of analysis that you're doing, it might be useful to approximate a polynomial of a higher degree with a polynomial of a lower degree. Okay, so we will start our discussion in this first part of the video with linear approximations. Linear approximations represented by linear functions, these are easy to manipulate. So let us now look at how we can find a linear approximation to an arbitrary function. Let us suppose we have a function f of x which is represented by the curve in blue here. The question is, what exactly is our objective here? The objective that we have in mind here is to be able to approximate this function with a linear polynomial at x equal to a. And a natural candidate for such an approximation is to use the tangent line, the tangent to the graph of the function at x equal to a. Now, for this, we will assume that the function is differentiable at x equal to a, because this is the math that we will need in order to work with the equation of the tangent line. So if you look at the equation of the tangent line at the point a comma f of a, that is given by y minus the y coordinate of the point, which is f of a, which is equal to f prime at a, and this is why you need differentiability. So it is equal to y minus f of a is equal to f prime at a times x minus a. So this is the equation of the tangent line at a comma f of a. Now this in turn can be written as y equal to f of a plus f prime at a times x minus a. So if I want to approximate my function here f of x by the tangent line, which is mathematically expressed as f of a plus f prime at a times x minus a, so I can write my function f of x approximately equal to f of a plus f prime at a times x minus a, right? And this then is a linear approximation to the function about the point a. Note here that we are going to be taking, for the purpose of our approximation, we are going to be taking x close to a, because as you can see here, for example, in this particular example, with the tangent line, because here we are also running into the risk of making errors. So if you are closer to a, your error will be smaller. So for example, in this kind of an example, we have that the farther you are from a, the larger the error would be. So you don't want to run into the risk of making large mistakes. So we'll stick to having x close to the point a, where the approximation is going to be carried out. Around this point, the approximation is going to be carried out. So formally, the linear approximation to the function f about x equal to a is given by f of x approximately equal to f of a plus f prime at a times x minus a, where x is taken close to a. Because here we also have that the function is nicely behaved, it's continuous, and we don't have big jumps in the function. So taking x close to a helps keep the error in check. Now this linear approximation is also called the first order Taylor polynomial approximation of f of x about x equal to a. So this is the Taylor polynomial of the first order, f of a plus f prime at a times x minus a, right? This is the first order Taylor polynomial, and this is what we are using as the approximation to the function about x equal to a. Now there are two things to be noted here. This polynomial that we are using, the first order polynomial, because it's a first order polynomial, this is linear in x. So our polynomial here is f of a plus f prime at a times x minus a, and clearly this is linear in x. So because we're doing a linear approximation here, this perfectly fits in our scheme of things. And further, this polynomial resembles a function f of x near x equal to a in two respects. First of all, if you look at this expression here, the value of the polynomial at a, what is that going to be? Because if I put x equal to a here, I'm going to get exactly f of a. And similarly, the derivative of the polynomial at a, which is going to be here f prime at a, because the moment you put x equal to a, the second term is going to vanish, and in that sense we have these two aspects, p of a is equal to f of a, and the derivative at a is also for p is also equal to the derivative of the function at a. Note that the approximation is exact at x equal to a. So what you can see here pictorially is also what I've just conveyed mathematically, which is that both the function and the polynomial approximation which we are using, which is a linear approximation or the tangent line here, both the function and the polynomial approximation, they have the same value at x equal to a, which is f of a, and also both have the same slopes at x equal to a, which is but natural, because the derivative of the function at x equal to a is nothing but the slope of the tangent to the graph at that point. So these are the two aspects in which the polynomial resembles the function f of x near x equal to a. The approximation is exact at x equal to a, and here in this context, in this graph, you'll see that you'll be making an error if you are away from a in the context of this picture. Now, this also sets a stage for carrying out higher order approximations. For higher order approximations, we can further argue that if we want a polynomial that should mimic the function at x equal to a, we would not only want the values of the function and the polynomial to be the same at x equal to a, but we would also want the derivatives, the first order derivative or the second order and the second order derivative or higher order derivatives, to be the same at x equal to a for both the function and the polynomial. So this would then take us to higher order approximations, and we will see in the second part of the lecture how mathematically also this is consistent with taking higher order approximations. Now let us get a sense of linear approximations through a few examples. Let's see how linear approximations work. The question here asks you to find the linear approximation to the function f of x equal to the cube root of x about the point a equal to 1. So you have to find the linear approximation. The function is x to the power 1/3. Now, as we have from the formula, for x close to 1, because you're taking the approximation around 1, the function f of x will be approximated by f of a. So because a here is 1, you'll have f of 1 plus f prime at 1 times x minus 1. I have simply taken the formula from the previous slides for the linear approximation, and the only difference here is that instead of a, I have 1 because I am taking the approximation around x equal to 1. So note here that we have a couple of calculations to do. So let's go ahead with these calculations. F of 1, because f of x is the cube root of x, so f of 1 is going to be exactly 1. Now f prime of x, in order to calculate f prime at 1, I'm going to first calculate f prime of x, which is nothing but 1/3 times x to the power minus 2/3. So this in turn implies that the value of the first order derivative at 1 for the function is 1/3. And this then gives us the linear approximation to the function, which is then 1 plus 1/3 times x minus 1. Now, the question further asks you to use the linear approximation that you derived in the previous part to estimate the value of cube root of 1.03. Now, this is going to make things interesting because here you start seeing the usefulness of Taylor's approximations. Then the question further asks you to compute the percentage error percentage error in the approximation. Now, if we look at the linear approximation, our linear approximation for the function cube root of x is given by 1 plus 1/3 times x minus 1, with x being close to 1. And if I want to estimate the cube root of 1.03, so basically this means that my x here, because if you look at the function that I have, my original function is a cube root of x, and because I want the cube root of 1.03, my x is nothing but 1.03, and this then can be approximated by 1 plus 1/3 times x minus 1, which will then become 1.03 minus 1, which is 0.03. And this then, because once you divide 0.03 by 3, you're going to get 0.01. So, this then gives you the estimate of the cube root of 1.03 as 1.01. Now, if you actually get your calculators and calculate the cube root of 1.03 using a scientific calculator in this case, you would get the value, the correct value as 1.0099, and you can clearly see that you're not off, you're hardly off the correct value, and we'll just look at the percentage error that we are making in the approximation. So, this is a pretty good estimate, 1.01, and this also gives us a message that sometimes, you know, when we don't have calculators, or if we don't have a scientific calculator, it is easy to use these kinds of principles, linear approximations or higher order approximations, to carry out our calculations. So, this is a smart way of doing it without using a scientific calculator. And let's see what exactly we have further. Here we are looking at the percentage error that we've made in our calculation. Any discussion of approximations is incomplete unless we talk of the error that we have made. And in fact, we can bring in the concept of a remainder, because see, we have an actual value and we have approximated it by a polynomial approximation. So, the difference, so if we look at the actual value which is given by f of x and the approximation which is given by p of x, the difference f of x minus p of x can be called what is known as a remainder. Now, we are not going to get into too much detail here about the remainder. This is something we will take up in the next lecture, which is going to be the 30th lecture, and there we will do the Lagrange form of the remainder in a lot more detail. We will also look at the upper bound to the error that we can make, and this requires a full class. So, typically we do it in a separate session. For now, let's do a more intuitive calculation, because whenever we talk of errors, it is natural to look at the percentage error, and the percentage error can be calculated here as the absolute value of the difference between actual minus approximate. So, that is telling us how far off we are from the true value, and that will divide by the actual value, the correct value, times 100. So, because we are looking at the absolute value, we can take the difference in any order. So, our approximate value was 1.01. I have taken that first because that is larger. So, from that I have subtracted the actual value, which is 1.0099, does not matter because we are looking at the absolute value in the numerator. That I have divided by the actual value, which is 1.0099, and that multiplied by 100 gives us a percentage error of 0.0099%, which is really tiny. So, this is a huge achievement, because this is something which allows you, this calculation is something that allows you to do things by hand rather than relying on a computer or a calculator. Now, let us look at another example to illustrate linear approximations, and here also we see some interesting twists. So, the question asks you to prove that 1 plus x to the power m is approximately equal to 1 plus mx for x close to 0. Before I move on, let me just mention that whenever we take the approximations around 0, that is also called a Maclaurin's approximation, or Maclaurin's polynomial expansion. So, that is something which is just a special case of the Taylor's approximation. It is the Maclaurin's approximation comes in when the approximation is around 0. So, our function here is 1 plus x to the power m. The linear approximation is given by f of x is approximately equal to f of 0 plus f prime at 0 times x, because x minus 0 is what you are going to have here. So, that is nothing but x. Now, let us quickly do our calculations, let us get our ingredients ready for our calculations. So, we have f of 0 equal to 1 when we put x 0 here, right? And f prime of x is m times 1 plus x to the power m minus 1. So, this in turn implies that f prime at 0 is nothing but m. And once we plug in these values that we have found into this linear approximation, we get f of x as approximately equal to 1 plus m times x. Now, what we are going to do next is we are going to use this result to estimate a few values, and again this is something that you can do by hand, and the first part of this estimation requires you to estimate the value of square root of 82. Now, the square root of 82 can be written as under root 81 plus 1. But let me also point out a common mistake that students tend to make initially when doing such problems. They tend to take x as 81, and they take it as they try to mimic that 1 plus x to the power m here. But remember here that x has to be close to 0. So, 81 is nowhere close to 0, you are far off. So, there is something more that you have to do, and this manipulation that I am going to make is what helps us get the correct, what helps us get closer to the correct value. Which is that when I take 81 common under the square root sign, I get 1 plus 1 by 81 in brackets. Now, because we know square root of 81 is 9, so that I can take out of the under root sign. So, I get 9 times 1 plus 1 by 81 to the power half, right. Now, 1 plus 1 by 81 to the power half. For this calculation, we can easily use the formula 1 plus x to the power m approximately equal to 1 plus mx. We can use this linear approximation because 1 by 81 is close to 0. So, that condition is fulfilled, and therefore, 1 plus 1 by 81 to the power half can be written as 1 plus half times 1 by 81, because our m here is half, 1 half. And this then gives us 1 plus 1 by 162, which is 163 by 162. But then remember, we also have to multiply by 9 because we had taken that out of the square root. So, once we multiply this by 9, we get 9.05555, and this when compared with the actual value, you can see the actual value is 9.05538. Again, you are very close. This estimate that you have got is correct up to 3 decimal places. So, that is a very neat estimate to get. Another estimate that I have asked you to get at is the 5th root of 31.95. And here also we will make a similar manipulation, because 31.95 to the power 1 by 5 can be written as 32. Because see, ultimately you have to get a 5th root. So, I know that the 5th root of 32 is 2. So, I am going to manipulate things in that direction. So, I have 32 minus 5 by 100 raised to the power 1 by 5, and here I can take 32 common. So, I get 32 times 1 minus 5 by 3200, the whole thing to the power 1 by 5. I can take 32 to the power 1 by 5 out of the brackets here and write this as 2 times 1 minus 5 by 3200 to the power 1 by 5. Again, we are able to now use a result 1 plus x to the power m approximately equal to 1 plus mx, right, because x is now close to 0. M here, x is 5 by 3200 and our m is 1/5. So, 1 minus 5 by 3200 to the power 1 by 5 can be written as 1 minus 1 by 5 times 5 by 3200, which in turn is equal to, because the 5 here in the denominator will cancel out the 5 in the numerator. This then is equal to 1 minus 1 by 3200, which is 3199 by 3200. Remember to multiply this by 2 for the final result, and a final result is 1.999375. Again, you can see the result that you get is so close to the actual value. So it's an amazing result. And imagine we rely on calculators so much, and because we perceive these as difficult calculations, and here we're getting the answers within seconds or a few minutes. Let us now look at an economic application of linear approximations. This is an example where we are assuming that demand is given by Q equal to 100 plus 4 times P minus 0.5 times P squared, with P representing price. And here we will assume that P is greater than or equal to 4, because this is a quadratic polynomial, and here to get a downward sloping demand function we need P greater than or equal to 4. Suppose this demand is to be approximated by a linear function. Let us suppose your analysis is such that it's easier to work with a linear function. The question then asks you, what is the linear approximation you would use for values of P around 8? So we have to take linear approximation around P equal to 8. Now our function we can define here, this demand function, we can define it as a function of price. So our original demand function is 100 plus 4 times P minus 0.5 times P squared. And here the linear approximation around P equal to 8 would be given by our formula f of P approximately equal to f of A, which is in this case 8. So f of 8 plus f prime at A, which is again A, because A is 8. So f prime at 8 times P minus 8. Let us now plug in the values. So f of 8 is equal to, we will plug P equal to 8 into the original demand function. So that then gives us 100 plus 4 times 8 minus 0.5 times P squared, which is 64. And once we do this calculation, this is going to give us 100 plus 32 minus 64 times 5 is again 32. And the 32 here, the second term will cancel out the 32 in the third. So f of 8 is 100. F prime of P is nothing but 4 minus P. So that's going to give us f prime at 8 as minus 4. Therefore, we can approximate the function f of P by 100 minus 4 times P minus 8. And this, if you solve further, if you simplify this expression further, you're going to get 100 plus 32, because minus 4 times minus 8 is 32. So that's 100 plus 32, which is 132 minus 4P. Okay, so this then gives us the approximation, the linear approximation to the demand function, and our approximated linear demand function is given by Q equal to 132 minus 4 times P. Actually, linear functions are easy to manipulate, and very often in our research or in our analysis, we like to work with linear approximations or linear functions. Let us now take up one more example before we end this session, and here we are required to use Taylor's expansion of f of x equal to the square root of 1 minus x around x equal to 0 to obtain an estimate of square root of 2. So this is also an interesting calculation. This is a problem I've adapted from some discussions I saw on the internet. So I have myself written out this problem. So here we are taking n equal to 1, the order of the approximation, it's a linear approximation that we need. Now there's a hint that has been given to you. Write the square root of 2 as square root of 98 by 49. Right? We can do it that way. And again, we're going to use that same kind of manipulation that we did a little while ago for calculating the square root of 82 or the other calculation that we did. So let's, basically we have to make sure that x is close to 0. Now, following up on the hint that we have square root of 2 is square root of 98 by 49. Now, because square root of 49 is 7, I can bring that out of the square root sign and write things as 1 by 7 times 100 minus 2, because 100 minus 2 is 98. And again, I can take 100 common because that has a clean square root. So that's going to give me 10 by 7 times 1 minus 2 by 100 to the power half. 2 by 100 is nothing but 1 by 50, right? Now, 1 minus 1 by 50 to the power half is going to mimic our 1 minus x to the power m, which is something we've already seen as being given by 1 minus m times x. So that's going to give us 1 minus half, because m here is half, times x, which is 1 by 50. That in turn is equal to 1 minus 1 by 100, or 99 by 100. Further, in order to calculate square root, the square root of 2, I'm going to multiply the estimate of 1 minus 1 by 50 to the power half by 10 by 7. So I have 10 by 7 times 99 by 100, which is 99 by 70. And this then is again 1.41428, which is correct up to 4 decimal places, and that again is a magical result that we have. So these are the kinds of examples that you should be working on. There are plenty of them available in different textbooks and also on the internet. So that's all we have for linear approximations. Thank you very much.